Hello and welcome to my presentation titled Exploring Black Holes, the Mystery of the Universe or Mysteries of the Universe. My name is Alondra Soto. I am from the course CIFI 4005 from the section 003 and today is December 1st, 2024. So to begin, I will talk about the table of contents of what I will be talking about in the presentation today. I will be giving a brief introduction, anatomy, formation, observational evidence, physics, unsolved mysteries, ongoing and future research, all surrounding black holes. And finally, I will provide a conclusion of all I talked about in the presentation and the references I used. So to begin with, I will be talking about what are black holes, basically. They are basically huge concentrations of mass, all compacted into very teeny tiny spaces. They are so very dense that the gravitational pull that they exert from its surface, also known as the event horizon that we will be talking about later, makes it literally impossible for anything to escape its grasp, not even light. And we will learn about that very soon. And just so you guys can get a better notion of black holes, a black hole could be the same size or even smaller than the sun, but that black hole can have 100 or even 1,000 times more mass than the sun. So it could be smaller in size, but have way more mass concentration than the sun. There are different types of black holes. The four main types will be stellar, miniature, intermediate, and supermassive. You guys are probably wondering what's the difference between them. Here I have a small table to compare them. I'm going to go through them. Stellar is between 3 and 100 solar masses. Intermediate is between 100 and 1 million, and supermassive is basically 1 million and above. So stellar, intermediate, supermassive, from smaller to larger or bigger in size. Here, again, still part of the introduction, this is the first ever image taken of a black hole. It was captured by the Event Horizon Telescope in 2019, and the telescope was pointing or observing the center of the M86 galaxy, and it is actually 6.5 billion times the mass of our sun. So it definitely falls or undergoes the category of supermassive in this case. And it seems very blurry, doesn't it? But although you can barely make out its outline in this photo, there has already been a whole understanding of the anatomy of black holes, which is what we'll be talking about in the next slides. For the anatomy of a black hole, I prepared this diagram. The image is taken from NASA website, and in here I mentioned various parts. You can see the accretion disk, Doppler beaming, event horizon, corona, photosphere, singularity. So I will be going a little bit in depth into them right now. First of all, the singularity, which is the theoretical point at the very center of a black hole, where matter is crushed into infinite density. So basically what is provoking that intense gravitational pull. Based off of that, the event horizon, which we can see, let me turn the pointer on, which we can see right over here. It is basically a boundary, or what other scientists and other articles have seen described as like the surface of the black hole, and where the velocity needed to escape it equals the speed of light. Also, there is the accretion disk with a hot disk of gas orbiting the black hole, and it's basically the main source of light. What scientists were able to picture and what I showed before. And based on the accretion disk, there's Doppler beaming, which is the effect that causes the different intensities of light seen in the black hole. If a certain part is rotating or spinning towards us, it will look brighter. If it's spinning away, it will look dimmer or darker. Also, I would like to mention the photosphere, which is basically a ring of light that forms around the event horizon. And additionally, there is the corona, which is a 10 billion degree cloud that just extends above and below the disk overall. As for the formation of black holes, before I get into these stages, the most common way for a black hole to form is due to the death of a star. However, not every time a star dies, a black hole is formed. Basically, a star must first go out with a massive explosion and turn into what we know as a supernova. At their center, there is a contact remnant that is left behind, which can turn either into a neutron star or a black hole. If it turns into a black hole, then its first stage would be the collapse, which we can see here. The collapse is when the star's core begins to collapse in on itself, because now that it's dead, there's no other forces opposing that gravitational exertion from the core. So it just begins to start falling in or collapsing into itself. When that happens and the collapse reaches to the point that it all compresses into an infinite point, then that is what we know as the singularity. And as I mentioned earlier, from the singularity, the event horizon arises because it depends on the mass and the size of the core, or the singularity. And finally, once all of this is formed from the black hole, the black hole in itself will have its characteristics, functionalities, such as stretching or curving, or what we have seen, the physics that we have seen around the black holes that have intrigued us so much. It doesn't only have to be stretching or curving or just turning around and this forming things that are physical. It could also mean the space-time. So very cool. Now we shall go to observational evidence for black holes. As for the observational evidence found, we have seen that there are gravitational effects exerted from black holes. It has been seen how black holes' gravity affects nearby stars, making them appear to be orbiting just nothing, or just clear space, which is not true, because we found to see that it is black holes' presence. There has been different detection methods, whether it be through using X-rays, gravitational waves, and the Event Horizon Telescope imaging, which is the image I have shown previously. And finally, there is a very widely studied supermassive black hole found or located in our galaxy, the Milky Way galaxy, known as Sagittarius A. Okay. Now for the physics of them. So how do they work, or what physical properties have they shown? The first thing is Albert Einstein's general theory of gravity. It's what basically supports or is the foundation of black holes overall. In this theory, Einstein states that gravity arises when both mass and energy just warp the fabric of space and time, which causes the trajectory of free-falling objects to curve. And just another term for this is space-time warping, or it's basically explanation as to why our Earth orbits around the sun. However, based off of this, only a year later, this theory was published. The physicist Carl, I cannot pronounce his last name. The physicist Carl deciphered the shape of the bit in space-time that the singularity of a black hole would create. He basically predicted what we now know as the event horizon. This is very important because it just brought more attention into what the event horizon contributes as to the black hole's functionality. As of this, it was found that at the event horizon, the escape velocity equals the speed of light. So in other words, once something crosses the event horizon, it cannot escape the gravitational pull, since anything faster than the speed of light has yet to be discovered. So if you were to theoretically gain powers and be faster than the speed of light, then maybe you could escape a black hole. But as for now, absolutely nothing in the universe can escape one. There was also found gravitational lensing and time dilation. Gravitational lensing is when light bends around the black hole, creating distorted images of distant objects. Time dilation refers to when something is near a black hole, time slows down significantly in comparison to distant observers. Now to one of the very unsolved mysteries regarding black holes. Where do they lead? There are many speculative ideas, but the two main ones would be wormholes and white holes. So wormholes are basically theoretical passages through space-time that could potentially be connecting distant points in the universe or just within the universe. The idea basically arises from the singularity, which is just the part where extreme space-time warping occurs. As for white holes, they are theoretically opposites of black holes. So if in black holes everything can get pulled in and no matter can exist there, then in white holes nothing can enter, but all there is inside is matter. This was basically predicted by Einstein's equations. However, there have never been observed in nature. These both are still extremely theoretical and just very much in a what if, because, for example, for wormholes to be transversable for us or just anything to be able to pass through them, exotic forms or negative energy would be necessary to stabilize it, which defies known physics. And as for white holes, the speculation is that they could lead to another universe or another very distant point within this universe, but there is still no empirical evidence to support this. As for ongoing and future research, right now, very recently, I would say literally 2 weeks ago, I found an article where a young physicist, Sophie Kurami, expresses that through her ongoing research on supermassive black holes and observations from the James Webb Space Telescope, some black holes, which she termed or just are termed overall primordial black holes, could be dating from the very early universe or even before the Big Bang. And she also expresses that these specific black holes that date so very back can have a greater efficiency or just very more efficient interactivity than others that date closer to our timeline. Studying this type of black holes could also include researching their interactions with dark matter, and just it could also indicate their role in galaxy evolution, or even so they might be or might have been large contributors into the creation of the universe in itself, which is very interesting. As for future research, scientists are very much looking forward to gravitational wave detector LISA, which would allow us to detect supermassive black holes at vast distances. It is expected to come online in the 2030s. This is very important because the ones that have been studied up to this date have been within our own galaxy or just near our galaxy, so we do not know much of black holes or supermassive black holes at large distances or large light years away. We also are looking forward to Event Horizon Imaging, basically just to be able to study the dynamic processes of the event horizon in real time, and just to gain more images, or hopefully more clearer images of black holes, besides the one that we have that is very blurry. So yeah. And finally, the interactions between black holes and dark matter. What could it mean between them, since we now know that dark matter makes up a large chunk of the universe. As for conclusions, we have seen or discussed the definition, types, anatomy, and formation of black holes. We saw that there are various ways to detect black holes, whether it be X-rays or gravitational waves, and just the way that stars orbit around them. We have also seen that the overall physics of black holes spark many theories around them, specifically as to what they lead to, whether it be wormholes, white holes, and just how they warp space-time overall. And we have also seen that black holes that date back to the very early universe could be or have been large contributors to the galaxy or even cosmic evolution. And finally, there is still more data needed on black holes that aren't from or near our galaxy. So with that, I will now show my references. This is where I got all my information from to realize this presentation. And yeah, thank you so much for tuning in and watching my video. Hope you have a great rest of your day or night or whatever, afternoon or whatever it be. So thank you so much. Goodbye.